autocovariance and use that as an example of where we might choose an estimator with better practical properties than one with better theoretical properties. So here's our tried and true gamma hat k, the sample autocovariance calculated as gamma hat k, where k is the lag, equals 1 over n, the sample size, times the sum of I equals 1 to n minus k of these cross products, xt minus x bar times xt plus k minus x bar, again, assuming a stationary time series. Now, this has a nice, or a not as nice, actually, theoretical property that this one's actually biased, that the expected value of gamma hat k is not equal to the population gamma, the population autocovariance. So that's not a great theoretical property, but it does have some nice practical properties we'll see here in a second. So what's another one? Well, another one that actually is unbiased is what we'll call gamma tilde. Gamma tilde sub k is equal to 1 over simply n minus k times the sum of I equals 1 to n minus k times xt minus x bar, xt plus k minus x bar, and this is unbiased. Tilde k, the expected value of that is equal to gamma k. Awesome. So, great. I'd like to use unbiased estimators when possible. However, let's check out some situations where this may not be advantageous. So we'll look at 2 here. First one, let's say that we go, I'm not going to put every mark down here, but let's say we go from 1 all the way out to observation 100. Cool. So we've got n is equal to 100 here. We'll call this xt, and this is time. Just for reference here, we'll say that's like 50. And there's 100 observations in there. Okay, and so let's say that we take our realization and we let our realization go. We let the process go. It generates 100 time points, values at 100 time points. And let's say that it starts up here at 6, and this is 0, and this is negative 6. Yeah, just to make our example here. So I'm going to start here at 1, we'll start at 6, and then let's say it just wanders around, goes up and goes down, wanders, goes down again, and then comes back up and ends right there. It ends right there. So let me connect it up. Okay, so let's say that it ended at 5. Okay, so that thing ended at 5 and it started at 6. Okay, so now if it's stationary, I'm assuming that every time point, each x1, x2, x3, all those random variables have distributions with the same mean and same standard deviation, same variance. However, we want to talk about the same mean. So if that's the mean, let's just say that the sample mean of all of these turned out to be, there's some high ones, there's some low ones. Let's say that it turned out to be 0, just to make my math easy, but it's possible. So let's say that that's what it was. That was x bar. Okay, fantastic. So we know this is wandering. If I looked at lag 1, right, almost every observation that's observation of the one before it, they're either above the mean, they're both above the mean, or they're both below the mean. Or they're both above the mean, or they're both below the mean. Occasionally you'll get ones that split, but they're so close to the mean, those values are so 0. They'll be negative in the cross product, but almost 0 anyway, like negative 0.0001 or something. In here, most all the time those products are positive, either negative times negative or positive times positive. So we know that this ACF, the ACF will, of course, be 1 at 0. In fact, let's make this the covariance. We're going to talk about covariance here. Let's just say that's covariance. I'm not going to put any values up here. In fact, let's do this. If I was talking about correlation, I'd make this go from -1 to 1. But we're talking about covariance. So I'm just going to keep it on the scale. I'm not going to label the scale. It's not important what the numbers are right now, just if they're positive or negative and kind of their magnitude. So I'm going to say that's covariance. And so that is the covariance, autocovariance. Autocovariance. And this is the lag. So the lag here will go from 0 all the way out to, we could go out, but we're only going to be able to calculate out to 99, right? Because if we have the observation 100 and we have observation 1, those are 99 apart. I can't calculate any bigger lags than that. So I've got 0 to 99. Now, the true, we'll say the true ACF, or that's will be some really big number, and then it will slowly damp until finally it'll be basically 0. Just saying that there's not much information about today from a time point 99 units ago. And that makes sense. The further we get on in time, the less the past affects the future. And that's certainly evident in this one. But this one just happened to wander and had to end somewhere, and it ended at a 5 and it started at 6. So if we calculate these things, we know we'd like to have an estimator that intuitively gives us something close to 0. But we note that, in fact, let's try it. So we do gamma hat of 99. Let's say we want to look at lag 99. I think it should be 0. It should be close to 0. Very close to 0. So in that case, it's not too hard to calculate, right? So I don't have much room here, but I don't think I need much room. So I'll just say that equals 1 over n, which is 100. And there's only one cross product, and that's why this is n minus k. So this is 1, I equals 1, and how many of those can I get? If k is 99, then that's just 1 to 1. And there's only one that we can have here, because that's going to be x1, and that's going to be x100, 1 plus 99. There's only one pair that's that far apart. So this will be, and the way I've made my example here, this will be 6 minus 0. So 6 minus 0 is, of course, 6. And this will be 5 minus 0. That'll be 5. And that will give us a grand total of 30 divided by 100. So that'll give us a grand total of 0.3. 0.3. Don't have much to compare it to right now, but 0.3 might relatively be close to 0. It's not 0, but let's see what the calculation of gamma tilde would be. So gamma tilde 99 will be equal to 1 over n minus k, where that is, k is 99 and n is 100, so that's 1 over 1. And this is all the same. So this would be 6 times 5. So that estimate is based on one pair of observations, and those could be anywhere. And so, and there's nothing to average them out. So that would be equal, of course, to 30. So just looking at it, this one, the unbiased estimator is not built to kind of force further back in time to become, autocovariances to become really close to 0, to kind of converge to 0. Because it just says, hey, whatever the last cross product is, that's my estimate. That's how I'm going to get my estimate of the autocovariance. So in this case, if it's just in this random case, it could be not only is it close to 0, it's really positive. It's not, or is it not close to 0? It could be really high, like 30. But let's say that I had another one, just to drive the point home. Is there's 1 and there's 100, just to show how dependent it is on just where this thing winds up. So again, if I had this as xt, and this is 6, and this is -6, and let's say that that is 0, we'll set it up pretty similar. We'll just have it end in a different spot. It's got to wander somewhere. So right here, it starts there, and it wanders down like it did before. Wanders up, wanders down, wanders up, and then it wanders up, and then it ends up wandering down. So it ends up right there. Okay. Well, same thing, right? Could just draw a line there, but why not? Let's just remake this, right? If this is the mean, let's say that's at x bar at 0, at lag 2, those points are almost always going to be below, or those two juxtaposed points are always going to be above. That's at lag 1. At lag 2, almost every pair of 2 are above or below the mean together. They move together. But eventually you get to lag 10, right? At lag 10, maybe it's here, 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 but then you'll get some significant values on either side of the mean. So you'll start getting some of these positive cross products canceled out by some negative cross products, which is why that damps. So this will be, again, at 0. We will let that go up. But as you get farther and farther away, the true autocovariances damp to 0. And by the time you hit lag 99 units ago, observations 99 time points apart, they're pretty much uncorrelated. And that's intuitive. That's what the true autocorrelation would look like for a lot of models that have this type of structure. So, so let's calculate it. So let's check out what this one is. Now this one, say this ends up, this looks a little bit like maybe -4. That one's in. So instead of landing above the mean, it just 50-50 at this point, landed below the mean. So this one here would be gamma hat 99 equals 1 over 100 times started at 6, but ended at, again, right, 99 units apart. So that's I equals 1, or up here, I equals 1 to 1. That's x1 minus 0 and x100 minus 0. x100 in this case is -4, so that is a -4, and that equaled -0.24. Okay, great. Seems kind of reasonable. And then let's compare it to gamma tilde 99, which equals 1 over n minus k, which is 100 minus 99, 1 over 1. So whatever we see here is what that estimate is going to be. So that's 6 times -4. Okay, of course, that is -24. And boy, does that have a lot of variance. It could easily be very positive. It could easily be very negative. It's just as likely to be kind of close to 0. But this one, gamma hat, forces it to have that practical behavior, have that behavior that we expect, that intuitive behavior, because it's dividing by a really big number the farther out, the more observations we have. So it kind of forces that covariance to something we know it should be for a stationary time series, which would be close to 0. So great job. Hope you had a lot of fun. I did. I'll see you in the next one.